Now that you've had some practice drawing out some more of these shorthand electron configurations and orbital notations, we're going to look at the ones that you should have drawn out. We're going to check your answers, but we're also going to count things like the energy levels, subshells, orbitals, valence electrons, and unpaired electrons for each of these. And we're going to start looking for some patterns. So the first one that I asked you to draw out was sodium, and for sodium you should have had that there were 10 electrons inside of neon and then 1 electron in the 3s subshell. Krypton looks rubidium looks fairly similar. We've got krypton instead of neon as our noble gas, but again we only need one more subshell, 5s instead of 3s, and there's 1 arrow in it. So for energy levels of these two, we have 3 energy levels and 5 energy levels. For subshells, for sodium, we've got 1, 2, 3, 4 subshells. And for rubidium, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 subshells. Orbitals, we take our noble gas, so that's 5 plus the lines, so that's 6. Noble gas divided by 2 plus any lines you drew. 36 divided by 2 would be 18, plus 1 more is 19. Valence electrons for each of these, there's 1 arrow in the outermost ring. And unpaired electrons, there's also 1 unpaired electron from each. Now from these two examples, we're going to move next door and go with magnesium and strontium. So for magnesium, again, the energy level is 3. And for strontium, the energy level is 5. Hopefully at this point you've realized that if they're next to each other or within the same row on the periodic table, it's going to have the same number of energy levels. Energy levels are determined by the period or the row. Subshells for magnesium, 1, 2, 3, 4. And for strontium, 1, 2, 3, 4, 5, 6, 7, 8, 9. If they're in the same region on the periodic table, like sodium and magnesium were, or like rubidium and strontium are, they're going to have the same number of subshells because the region or the block of the periodic table is determined by these subshells. For orbitals, again, we're going to take the noble gas divided by 2 plus any lines that have at least 1 arrow, so that's 5, 6, and that's 18, 19. Because both sodium and magnesium, as well as rubidium and strontium, were just filling into the same lines that were already there and already occupied, the orbitals didn't change. Valence electrons for each of these, there's 2 arrows above the highest principal quantum number, and unpaired electrons for each of these are going to be 0. So if we compare elements that are in the same row across the periodic table, we notice that the energy levels are the same. If we compare elements that are within the same region within those rows, the subshells would also be the same. But the valence electrons and unpaired electrons aren't going to be the same based on the row. Instead, they're going to be same based on the column, what we call the group on the periodic table. Both of our elements that were in group 1 had 1 valence electron and 1 unpaired electron. Both the elements that were in group 2 had 2 valence and 0 unpaired. Let's jump over to group 13, which is where aluminum was. It's still on the 3rd energy level. 1, 2, 3, 4, 5. It's now added 1 more region, so that's 5 subshells. For our orbitals, we take our noble gas divided by 2 plus the line, so that's 5, 6, 7 orbitals that are occupied. Valence electrons are going to be all of these electrons that have at least 1 arrow above the biggest number, so that would be 1, 2, 3 valence electrons. And unpaired, we've got 1. Now we're comparing that with yttrium, which was the next one after strontium. but it's in a different region. It didn't go over to this P block because now we have this D block between it. So energy levels are still going to be the 5 because that's the biggest number. Subshells, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's in the 10th subshell, which was one more than the last. That makes sense. Orbitals, 36 divided by 2 would be 18, 19, 20, 20 occupied orbitals. And valence electrons, the valence electrons are actually going to be over here because 5 is bigger than 4. These are not valence electrons. So there are 1, 2 arrows above the biggest number. And unpaired electrons, there's 1 electron that is not a valence electron this time, that is unpaired. We want to compare this to silver, which is within the same row, and it's within the same region even, the 4D region, but it is further over on the periodic table. And we want to see if, by going to silver, have we added any more valence electrons. So energy level, biggest number is still 5. Subshells, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, didn't change, still 10. Orbitals, 36 divided by 2 is 18, 19, 20, 21, 22, 23, 24. 24 orbitals are now occupied. Valence electrons, the biggest energy level is 5, and there's still only 2 electrons on that outer ring. And then unpaired electrons, all the way at the end, we have 1 electron that doesn't have a partner. We want to take this idea and expand it to the entire periodic table so that we don't have to continue drawing everything out in order to figure out our valence electrons and unpaired electrons. And in order to do that, we need to start with this realization that if you are within the same group, the arrows look the same. It's just on a different energy level. And within the same period, the actual energy level doesn't change. So I'm going to look at our entire periodic table. And I'm going to pick a period that has the S room, the D room, and the P room in it. And I'm going to realize that I could then translate this to any of the other rows, even the ones above, but I just wouldn't have the center section at this point. So I'm just going to draw out a generic S, a generic D, and a generic P that I could then really fill in any numbers for. So for this one, I've got 4S, 3D, and 4P, but I could change those green numbers and make it work for any of them. Think about group 1. Group 1 is the first group on the periodic table. It would start with some noble gas, which in our case would be argon, and it would add 1 more electron in. If we add 1 electron in, how many valence electrons are there at this point? Well, since the 1 electron we added in is above the biggest number, that would be 1 valence electron. How many unpaired electrons are there at this point? Well, since that 1 electron doesn't have a partner, there is 1 unpaired electron of this as well. So all the elements in group 1 are going to have 1 valence electron and 1 unpaired electron. Now think about the elements in group 2. So for calcium, it would look like this, but really we could just replace the noble gas and these numbers and make it any element in group 2. All the elements in group 2, how many valence electrons do they have? How many unpaired electrons do they have? Elements in group 2 have 2 valence electrons and 0 unpaired electrons. All the elements in group 2 look kind of like this. They could just have different numbers down here for their principal quantum number, but all of them have the 2 valence and 0 unpaired. What about when I add another electron in to make scandium? Does that affect my valence electrons? Does it affect my unpaired electrons? Elements in group 3 here, that's group 3, are going to have still just 2 valence electrons. This is not a valence electron because it's in a smaller principal quantum number than the outer shell. So, elements in group 3 still only have 2 valence electrons, but they do have now 1 unpaired. How is that going to change as I go to groups 4, 5, 6, 7, 8, 9, 10, 11, and 12? Which of these numbers will change and which of them will stay constant? As I go to elements in group 4, 5, 6, and 7, I'm adding more unpaired electrons. So my unpaired electron count does go up. It goes 1, 2, 3, 4, 5. 5 unpaired electrons in group 7. But my valence electrons haven't changed because nothing was added to a 4 yet. So the whole way across, the only valence electrons these guys have are back over in this S block. So the valence electron stays consistent with 2. Now, once I get to group 8, I'm adding in electrons that are now facing down. So I'm actually getting less unpaired electrons. Now there's only 3, now there's only 2, now there's only 1, and at that point there would be 0. So the unpaired electrons, as I continue across my period here, go 4, 3, 2, 1, 0, but the valence electrons still haven't changed because I haven't added anything until my 4th floor, or the highest energy level. Once I get to group 13, now I'm finally adding things in again to the biggest number because the 4 was our biggest number. So now I have a total of 1, 2, 3 valence electrons. And if I look in group 13, there's one arrow that doesn't have a partner. So here we would have 3 valence electrons and 1 unpaired. When I add the next electron in, that's 1, 2, 3, 4 valence electrons and 1, 2 unpaired. When I add the next one in, I now have 1, 2, 3, 4, 5 valence electrons and 3 unpaired. And then, as you might guess, the next valence electron that goes in is going to pair up one of these. So now I only have 2 unpaired, and then 1 unpaired, and then 0 unpaired. All of those were valence. So that goes 6, 7, 8. And the unpaired goes back down to 0. And because all of the elements that would be within the group on the periodic table with these elements would have the same general configuration, they would just have different numbers here, these numbers really work for every element in the groups that we will be looking at. So you can very easily sketch out a periodic table and use the periodic table to determine the number of valence electrons and the number of unpaired electrons. So if there's my quick sketch, the valence electrons go 1, 2, everybody in the middle has 2, 3, 4, 5, 6, 7, 8, and the unpaired electrons go 1, 0, 1, 2, 3, 4, 5, 4, 3, 2, 1, 0, 1, 2, 3, 2, 1, 0. They basically count up based on the number of lines there are in that type of room, and then count back down. So D had 5 lines, it counts up to 5 and then back down, and S has only had 1 line, so it just goes 1 and 0. And that's how you can use your periodic table to determine both the valence electrons and the unpaired electrons for any element within the first 5 rows. Let me know if you have any questions.